Okay, so good evening, everyone. So today we present the third talk in the talk series, Podartha Bigyanar Itu Hitu Aru Bohutu. We heard about gravitational wave astronomy and black holes in the previous two talks, and so today we are going to get a different flavor that is of observational astronomy. So we have among us Mr. Debasish Hazarika, who is an observational astronomer at heart, as far as I know. He completed his BS and MS from Guwahati University Institute of Science and Technology, and then worked for a brief period as a research assistant there. Thereafter, he moved to the Institute of Astronomy and Planetary Sciences, affiliated to the University of Atacama at Copiapó, Chile, and he's been pursuing a PhD there. So he will mainly be talking about some of the recent developments in the field of observational astronomy and data analysis techniques. So we are excited to hear from him, of course. So participants may interact with him in either English or Assamese, so it's up to you. So no issues. So I think over to you. You can start the talk.
Okay, thank you, Himanshu. Uh, Thank you for the introduction. So, hello everyone. Myself Debasish. Today, I will be talking about some of my experience here, as well as the observational astronomy as a whole in the era of big telescope. So, my topic is what is in the sky, observing stars, galaxies, and exoplanets in the era of big telescopes. Okay. So, as we all know that astronomy is the very oldest or the ancient science. It was started actually since the prehistoric era. So at that time, some of the cave art that was discovered now or in the later times suggests that there are some ancient records of astronomy. So that time, those people actually used some animal symbols representing the star constellations in the night sky, and also used to mark some dates and events such as the comet strikes or the some related objects. So in this picture you can see that uh, there is an image which was actually uh, recovered in a cave in Europe. So in this picture, actually, they have calculated, they have actually put some mark to count some, probably some time or some date or probably some countings. So to mark some events. So this was the beginning at the time. Then they have started drawing some images that they see in the sky, and later that is that uh, cave parts were recovered, and finally the scientists have came to know that this was the beginning. So actually those time uh, they did not have any other assumptions or any other pre-knowledge about the nature. So whatever they saw in the nature, they actually started drawing that. So here we can see that uh, in a cave painting, actually it was recovered from the Magura cave, Bulgaria, which actually dated back 14,000 years ago. So here we can see one picture which contains some structures or some objects which looks like some sun or some other things. So later the anthropologists actually they have decoded this like this. So in the central part, probably that could be the sun, and then it's surrounded by some small other uh, art elements which were probably uh, the movement of the planets or the uh, other uh, other stars. So if we put those things in one line, then we can see that this actually forms a uh, one side is like for the moon, and another side is for the another season. So from that, actually, they have derived that probably that was the starting of that. They came to know that it is probably the season. So this was an interesting thing. So here it is described in the picture. So I, while preparing the talk, actually came to know about this thing. So it was a very good learning for me also. And so also they put some uh, marks which actually, as I mentioned, describe some of the events. Probably these events they were marking it as a lunar cycle. So later, when the idea of actually human civilization began, then people can take care of their primary needs. Then they started thinking more about the nature. So this is the evolution, like from the very beginning to our present time, when it started um, uh, evolving, the humankind, when it started evolving, then the basic questions actually comes, that what is in the sky. So there are two scenarios. One is in the daytime scenario, and another one is in the nighttime scenario. So in the daytime scenario, basically, we have sun, clouds, uh, these type of things in the sky. But in the night sky, they at that time they could recognize the moon and some stars, and they sometimes see some comets or some other shooting stars, but they were not sure about those ideas. So that bigger section remained like a big void for them. Later, when the civilization has started, the recorded evidence was actually found from the Babylonian civilization, who first recorded the Halley's comets in 164 BC. So this was the first evidence of recognition that astronomical phenomena are periodic, and of the application of the mathematics to their prediction. So that time actually the Babylonian also prepared some catalogs of stars and constellations, as well as some schemes for predicting uh, the rising and setting of the planets, as well as the precise calculation of the daytime or the month or the weeks, using some of their techniques, like some water clock or some shadow clock, etc. So later, in our region, actually, the Indus Valley civilization, when it started, then actually they were able to accurately measure the length, mass, and time and of the objects. So that time actually, Nalanda University started uh, the astronomy course, and also uh, they have actually developed some lunar calendar, and some of the most uh, talented people, actually they have come up, like Aryabhatta or Barahmihir or Brahmagupta. Those people actually they have accurately calculated many astronomical constants, such as the periods of the planets, times of the solar and lunar eclipses, and the instantaneous motions of the moon, like this. Later, Bhaskara, actually, he was the in charge of that Jantar Mantar. Now we call it. Now we can see in the Jaipur. So it was the actually first one of the world's most accurate pre-modern observatories. So that it contains more than 15 instruments, or like um, we can say some pillars or some round or circular shape instrument, which was used at the time to calculate precisely the uh, time the earth takes to orbit the sun, or like some other longitude latitude measurements, etc. So during the Renaissance, actually, when the uh, Copernicus revolution actually started, that's actually at the time the ancient Greek actually took astronomy. Actually, they have blended the uh, concept developed by various mathematicians, or and the concepts of the geometry and the physics, to study the nature, and they have tried to describe the astronomical events using those mathematics and geometrical concepts. So that time actually they came to know that planets revolve around the sun and the heliocentric picture that come up. And later some the similar kind of developments were also there in which can be seen in the Egypt, China, and Europe also. Later, uh, Galileo Galilei and Johannes Kepler's actually they Isaac Newton etc. They have actually improved upon the works of those Copernicus and those previous researchers. So here we can see that actually they were at the time they can mark some bright stars, and that group of bright stars forming actually recognizable patterns, and actually they call that as constellation. So the whole movement of the earth and the sun and the moon for one complete year, actually they have divided the whole patch of sky into a 12 regions with 30 days in each zone, along with the path uh, of these three objects like sun, moon, and the earth. So actually, they first the Babylonian actually first thought that as like some animal cycle, and because those stars they have actually connected to each other, the bright stars actually they are trying to relate it with some of the shapes of their animals. So most of the uh, constellations were actually like this type of shape, and that was one of the interesting point, because at this moment actually the idea of the zodiac sign also begins. And also after that, later in the 1600, there was a big uh, revolution, I would say, and there was some people who were developing some uh, glass and the mirrors and lenses. Actually they have used those things to develop some telescopes. So basically actually there was one person who known as Janssen, who actually developed uh, first telescope, but there was it is believed that he actually developed the first telescope, but there is no documentary evidence confirming this. And later, the Thomas Herrick, he was a scientist and astronomer living in the Oxford, and then he actually claimed that uh, that he first developed the telescopes and also observed some stars. But this was also not so well documented. So later in 1609 probably, yeah, so at the time Galileo uh, developed his uh, own telescope and started started observing the night sky. So this was the actually first documented evidence of use of the telescopes, and that we can see in the picture. This is the telescope image. This is the telescope of the of Galileo Galilei, and who first actually uh, observe when he started observing. Actually, he came to know that the moon has the craters, and also he discovered the sunspots, the moons of the Jupiter, and the phases of the Venus. So those ideas were very new at the time, and it has actually revolutionized the whole astronomy and our view about the uh, sky. So at the rightmost corner, at the rightmost picture, we can see that the picture that was sketched by Galileo and the observations of the moon revealed that there were mountains on the surface, and we can see the shaded region also. So this was the very first revolution. And after that, actually, the capturing of the light actually first was a big milestone at that time, and when one chemist who was known as the John Draper, who was the founder member of the American Chemical Society. He actually developed some techniques, chemical techniques, to capture the images. So this was the starting of the photographic film. So he actually, after that, he actually observed the uh, solar spectrum also, and also the picture of the moon. There you can see, and this was the very first moment when the uh, humankind has captured the light. So after that, actually before that, the pre-photography time, actually data recording of the astronomical uh, observations was limited to the human eye only. As we can see that in case of Galileo Galilei, whatever he observed, he just drawn by his hand. But at this moment, the humankind has captured the images in the real uh, of the real observations. So after that, actually scientists uh, started to think in a different way, and they have begun actually discovering the forms of the light which were invisible to the naked eye. Those were well known as like X-ray, gamma ray, radio waves, microwaves, etc. So also there was one very big uh, breakthrough at that time, was that when they started observing some other stars, they came to know that the um, composition of the other kind of stars are also similar to our sun. Only the changes are in terms of the temperature, masses, and sizes. So these were some big breakthrough at that time. And at the similar time, actually, there are some other kind of developments that were put forward by some other scientists like Maxwell or uh, Hertz. Actually, they have proposed the idea and showed that the electromagnetic nature, they have actually developed the idea, and they have proved that then when electric field and the perpendicular magnetic field are there, they can put each other, and it can propagate a wave that is known as the electromagnetic wave, as we all know about that thing. So they also, after that, actually they Maxwell actually proposed, and he showed that the light is nothing but an electromagnetic wave. So later it was experimentally confirmed, and the discovery of the radio wave by Heinrich Hertz in 1886. So in the picture, we can see that how they are propagating. These are, I think, the students can already studied. Students have already studied in their courses. So in the wavelength, actually, as we go longer, we have the radio wavelength. Uh, as we go towards the shorter wavelength, we have the gamma ray, X-ray, like this. And in the visible window, actually, that is a very tiny window. So before discovery of this electromagnetic wave nature of light, the idea of the um, light was actually limited to only the visible light, and they, after the discovery of this, actually the humankind has actually came to know that there are some other invisible lights also which can be used to probe the universe. So here we can see that this is actually a the spectrum of our sun, uh, which actually uh, shows like different ranges of uh, electromagnetic radiation. Actually, although the sun actually emits radiation at all wavelength, at approximately like near to 40% falls within the visible light wavelength. So when the evolution of the capturing of light has started, then the uh, scientists actually started to explore the other wavelength bands, and that those wavelength bands become like a new window to observe the universe. So here we can see that the opacity map of this of all other wavelengths. and you can see that from the ground we can only see at the optical and the radio fairly easily, and we can see very little opacity towards the very little transparency towards the uh, infrared. So it is difficult to observe infrared and ultraviolet, although they pass here little bit. So mostly in the world, actually in the ground level, we have the optical and radio telescopes, although some infrared and ultraviolet telescopes are also being developed. So it requires very sophisticated instrument with very high sensitivity. Okay, after that, um, when the semiconductor uh, revolution has been put forward, that time actually the scientists they have developed one interesting um, another device which is known as the surge couple device, which actually produce the surge when the photons strike their surface, and we can uh, understand the whole idea as a combination of some buckets which are collecting some raindrops. So here in this picture you can see that we have an array of 5 by 5 array of some buckets uh, which are collecting some raindrops. Then for each position, like row wise or the column wise, we can collect the uh, water amount, and we can put it as a matrix. So here in the matrix we can see that uh, the collection of the water is recorded, and the similar way actually the CCD works, which can read the surge which was created through the when the photon strikes, and that can be read digitally using some electronics. And that was the very basic idea of the digital capturing of the images. So we all now have the mobile phones cameras which contains the CCD chips, and similarly the same idea actually with more sophistications and more accuracy, maintaining more accuracy. Those CCD chips are used in the telescopes. So they actually from this picture, the analogy with the analogy of the uh, raindrops collecting buckets, we can understand the basic idea about the CCDs. So this is another breakthrough in the human evolution. And now we can see in this picture there are some raw images in the left, which actually was directly captured by the CCDs when we point towards the sky. And here we can see that there are so many artifacts are there which needs to be corrected, and there are steps, some standard procedures needs to be followed. And finally, when we follow and perform those step-by-step procedures, then we get actually the corrected image. Once we have the corrected image, then we can, there are some procedures we can follow which can actually fit some apertures to each of the brightest objects or points, and then we can select the stars. And when these steps are properly followed, we can have the data in the digital form, or like in the numeric form, we can say here, because already the image is in digital form. So we can extract the numerical values or the data in numeric form from the final corrected image. So here in this picture, we can see that how the data look like. The whole images actually get converted to some numeric data, and when and similarly for each and every night or each and every time, actually according to our need, we can collect the data. So for each and every image we have a time information and as well as the magnitude information, and then we can construct the magnitude versus time plot that is known as the light curve. So That is one example. I will describe it more detailed in the while I'll be talking about the variable star. So another interesting point was that actually we can observe like both ways. Like we can directly capture the light, or we can uh, take the spectrum. So in this picture, we can see that when we can capture the light as a spectrum, then actually we have many more information about the hidden information about the stellar system. So here we can see that the sun spectral line, which contains some absorption phasors, which are the dark lines. But in reality, actually, um, when we intuitively think, then we can think that the sun is the brightest object. It is emitting light, and how we can get this kind of absorption lines. So that is because the photosphere of the sun actually that uh, blocks some light that is coming from the core of the sun. Or same thing happens with the uh, different stars or the stellar or the cosmic objects. Actually, according to the availability of the elements, we can get the blockage of the light, and finally uh, the absorption phasors are being seen in the spectral line. And in this picture, we can see the sun in different wavelengths. Like when we see the sun in radio wavelength, and then we see different kind of features. When we see it in the ultraviolet, then we can see some other features like the stellar flares or the spots. And also in X-ray, we can have the information about some uh, photosphere or the inner core. So that means using the spectroscopy, actually we can conclude or we can get to know about that their chemical various chemical elements or the chemistry of the stars, we can say. So when people started looking like this, and then uh, actually they were able to classify the objects or the stars based on their element abundance, or like nature of the light, and some other external criteria. And finally they have classified the stars into different categories. The one most popular is like among them is the variable star, which I'm particularly or personally interested. So the variable stars actually that can be divided into many different categories. Here we can see this is known as the variability tree, which actually says that there can be two kind of variable stars. Basically, one is the extrinsic and another one is the intrinsic. The intrinsic variable stars are those variable stars which actually changes their brightness throughout the time uh, because of some of their intrinsic properties. For example, the sun. For example, the star that is undergoing nuclear fusion. Actually, if the fuel inside the inside the star, actually they are being exhausted. That can be one cause, or some other causes are also there. But in case of extrinsic variables, actually that should be some external criteria or the reasons. That could be something like there are two stars which are rotating each other. So one is blocking the when we observe that when they eclipses each other, then we see some dimming of the light. So that can be another kind that is known as extrinsic variables. And also there have many sub classifications among them. So basically based on those things, the scientists that actually uh, they have uh, they have put the they have constructed one diagram to classify the stars, mostly that is known as Hertzsprung and Russell diagram, that is known as HR diagram. So in this HR diagram, we can see that actually there are luminosity and as well as the temperature that is plotted. In the x-axis we have the temperature. In the y-axis, we have the luminosity of the stars, and we have many different regions in the HR diagram. So some regions are some actually we can see that there are some uh, diagonal lines or the regions which are known as the main sequence, which is coming from like this 4 in the luminosity to the 4 in the temperature in the x-axis. That diagonal line, that is known as the main sequence, which actually where the star spends most of its time. Similarly, after that, actually, when they run out of the hydrogen fuel and they started burning the helium fuel or the helium element, then they go to other branches. Like we can see, like in the upper part, you have the giant branches. So they really go towards those things. And in between them, actually, there are some instability steps, which are known as, which contain some stars which shows high variability. So among those stars, actually, there are stars known as the RR Lyrae or the Cepheid variables, which actually pulsates radially. So pulsates means that means they are pulsating. That means their radius or their radius is becoming bigger and smaller periodically, and that affects the luminosity of these stars. So these these type of stars are known as pulsating variable stars, which have actually got some particular interest because they have a very well defined period and luminosity relation, and which can be used as actually calculating the distances. That is a very important point here. So also they can be used as a uh, cosmic laboratory to study the stellar evolution, as well as can act as a tracer of metallicity, and structure of the host galaxy can be known those from the location of those stars. Also, they can be used as astroseismology candidates. So, like the seismic wave we have, like the earthquake, the stars also have the starquake, we can say. So that can tell us about the interior core of the star. So these pulsating stars actually, as uh, they are changing their radius as well as the luminosity within a very short period of time. That's why they can be used as a very good candidate to study, to know about their internal force, uh, and that's why they are known as the astroseismology. And also in the lower picture, we can see that uh, the distance. This is known as distance ladder. The uh, astronomical distances actually they cannot be computed directly using one type of technique, because for different ranges of distances we need to rely upon different kind of astronomical objects. So that is known as distance ladder. So you can see that for very nearby distances, we can rely on the radar analogy or the radar to probe to get the information about the different distances. Then we have the parallax. So uh, we can observe one star along with their backgrounds from two different positions in our Earth orbit. Say within 6 months, we can observe uh, the same star from within 6 month gap, and with respect to their backgrounds, whatever angle they actually forms, that can be used to detect the distances to those stars. But in the later but if we go beyond that distances, those distances which are very nearby, we cannot rely on the uh, parallax methods, because parallax calculations for larger distances will give us very small angle differences. So that will be not so good or accurate. That's why we rely on some other candidates. So in that case, the role play of these type of pulsating variable stars comes into play, and as they have a very well defined period luminosity relation. That means if we can measure the period of those stars, we can say about their absolute magnitude or the luminosity. And whatever we observe, that is known as the apparent magnitude. And if we take the difference between that absolute magnitude as well as the uh, apparent magnitude, we can get the information about the distance modulus. Again, we need to do some corrections for like extinction or the reddening, but in general we can um, calculate that way. And this is a very, and that uh, method, that is known as the standard candle method, because we know the uh, period as well as luminosity of these stars. And after that, if we move towards the uh, higher distances, we have to rely on some other kind of standard candles. Those were known as supernova, and also some other kind of techniques are also there, but I'm not going into those things now. So here we can see that these are some light curve of some variable stars like Cephids or RR Lyrae. And here we can see that they have different kind of shapes behave depending upon their stages of evolutions, and that uh, and those shapes, they are varying in shapes as well as in period. You can see for the extreme left panel we have higher period Cephids, but for the right panel we have the little bit lower period Cephids. So from this observational data, the light curve, one can conclude one thing, that the light curve shape actually, which is a very critical or very crucial parameter to describe to study about the about this type of stars. So basically, to deal with this, actually various mathematical idea or mathematical uh, theories were proposed, and also existing mathematical or statistical tools were used to to study the light curve shapes, and from the light curve shapes to know about the light. And similar kind of another process is like this, as I mentioned, that if two stars are there and if both stars are uh, rotating uh, each other, then if we observe the light curve, if we observe the light, then we can see that when they get eclipses, and then at the time we have some lower amount of light, and when the uh, star goes back to the another star, that is known as the occultation in astronomical language. That time also we can have some other dimming of the starlight. So one is the the big deep part, that is known as the primary eclipse, and the other part is known as the secondary eclipse. So this is for binary stars. These are not pulsating, but they are rotating each other. Or sometimes it may happen like one star may be pulsating and another star may not be pulsating, but they are rotating each other. Then also the scenario becomes more complicated. So basically, I'm talking about the pulsating stars. So to study the pulsating star light curve, actually one very well-known method is to uh, decompose the light curve into some Fourier, discrete Fourier, using some discrete Fourier transformation. We need to decompose the light curve into their periodic uh, elements. So the basic idea is that if we have a periodic signal that can be expressed in terms of sine and cosine, mm, and but in this case, what happened is like when we convert the in the first equation, you can see that when we convert the magnitude as a Fourier function of this form, um, we have some parameters like known as the Fourier coefficients. So those Fourier coefficients actually, in this case, highly depend on the uh, shape of the light curve, and thereby towards the various physical parameters of the pulsating star. And also we can see that when the star is becoming bigger in radius, their color is changing. They are becoming redder, and they are becoming red giant. And when they are going, uh, their radius is going shorter. That means the star is squeezing. At the time they are becoming blue color. So there are some mechanisms proposed actually to understand this behavior of the stars, and one popular mechanism is known as the kappa mechanism or the opacity mechanism, which actually tells us how this thing happens. Like when the star radius become shorter, it is actually because of the gravity. The Actually there is a tug of war going on that actually goes on between the gravity as well as the radiation pressure of the star. When the radiation pressure become higher than the gravity, then the star uh, become larger, and at that moment actually the radiation releases from the star surface, because the star surface actually that opacity that becomes low, and at the time the gravity actually started squeezing the stars, and at the time the star again their radius become low, and when the radius become low, their surface density or the opacity, you can say in this case actually that increases again, that results in the uh, expansion of the surface or the increase of the radius, and this way the star actually start pulsating. So what actually these Fourier parameters actually tell us actually is that we can see that there are mainly two kind of thing that describe the uh, that can be extracted from the Fourier parameters. One is the Fourier phase parameters, that is the phi term here, and another one is the uh, amplitude parameter. We have the A0, that is the uh, amplitude, and AI, that contains the amplitudes of their harmonics. So the Fourier phase parameter actually depends on the acuteness of the light curve, and the acuteness is actually measure of the time the light curve spent below the mean brightness and compared to the time spent above the mean brightness. And uh, another term is the amplitude, which actually describes the skewness of the light curve, which is the measure of the time while the star gets dimmer in comparison to the time while it gets brighter. So these things are actually related. These actually Fourier parameters can again be related to some of the physical parameters of the stars, like metallicity and some uh, other pulsation constants. So this way actually these Fourier things are very important. Now, as I'm talking uh, about the stars about the Cepheid stars and early kind of stars which are pulsating. There is another interesting historical scenario was there, which actually we need to put some eye on, and that actually is the basic idea is like when the Cepheid variable star was first discovered. Actually, at that time, uh, that Cepheid variable star was actually discovered in some other galaxies. Then only we can know about that. Beyond Milky Way also there is uh, something is there beyond the Milky Way also. So this idea is like this. Before 1920, actually there were two ideas proposed by two scientists. One is Captain, another one is Shapley. So Captain actually was the first one who thought that the sun is the center of the universe, and Milky Way center is the sun. So he at the time thought that the universe is limited to our Milky Way and sun is the center of the universe. But after that, actually, the astronomer or the scientist that Shapley came, actually he observed some other kind of uh, clusters. That means that contains more number of stars, and then he realized that our uh, sun is not at the center of the Milky Way, because he observed some more dense cluster of stars in the uh, opposite side of that center point. So he actually argued that uh, no, actually the universe is not limited to our uh, Milky Way, but maybe there are some extensions. But he could not confirm that there is something beyond the Milky Way. So in 1920, actually, there was a very great debate about one object in the sky that is known as the Andromeda Galaxy now. So at that time, Andromeda Galaxy actually was observed. That can be seen from now also. That Andromeda Galaxy can be seen using the naked eye. So people at that time, or the astronomers, actually they were thinking that the Andromeda Galaxy, that they told this as a Andromeda Nebula. So they thought that some astronomers thought that the Andromeda Nebula actually was part of Milky Way, and another thought that Andromeda Nebula was not a part of Milky Way. So that was a very great debate going on at that time. And in 1923, Edwin Hubble actually, he was observing the sky, and he discovered one cepheid in that Andromeda Nebula. So then he realized that it should be some objects which are beyond our Milky Way. So that's how actually the idea of uh, the galaxies come. So that is another breakthrough or the surprise to the humankind. So we can at that time only, like 100 years back in 1923, we had the idea about the galaxies. Before that, we did not have any solid idea about the galaxies. So here we can see that only actually from the uh, through our naked eye, actually we can see only three galaxies in the sky. One is known as the Andromeda, which is far bigger than Milky Way, and another two are the large Magellanic Cloud and small Magellanic Cloud, which cannot be seen from the northern sky, but from the southern sky these are visible. So this picture, actually the left side picture, actually these are the view of the Magellanic Cloud, and that can be seen using the through the naked eye. And in the right picture, right sided picture, we can see that which are very visible from through our naked eye. And these are the things. The larger one is known as the large Magellanic Cloud, and the smaller one is known as the small Magellanic Cloud. So these are known as some two satellite galaxies of Milky Way, and I'm feeling excited to share this image because it was captured in Atacama Desert in an astronomy camp. And interestingly, I was during my undergraduate and masters, I was working on these two galaxies, and I never thought at that time that I will ever get a chance to see that through naked eye. But this time we are seeing this through naked eye. So once the uh, once the actually idea of this uh, multi-wavelength study begins, then we can see uh, our Milky Way through different uh, wavelengths. So this is the picture of the Milky Way, and we can see that if we observe the Milky Way at different wavelength, then we can see that we can get about different kind of uh, features. And it at one wavelength, if some feature about the gas is coming out, at another wavelength some features about the uh, disk part of the Milky Way, or the core or the bulk part of the Milky Way is coming out. So from this we can say one thing, that the object that we observed uh, actually again depends on the wavelength. So at what wavelength? At one wavelength, we can have some different kind of shapes, and another in another wavelength we can have some another kind of shapes. So this is actually typical uh, schematic picture of the Milky Way, where we have the bulbs as well as the Milky Way nucleus, or you can say it is actually uh, typical example of a components of a galaxy. We have the thin disk, thick disk, and other uh, dark matter halos are actually everywhere, and we have some globular clusters which are scattered throughout the uh, galaxy. And when astronomers started looking at different kind of galaxies, different kind of galaxies, mostly at that time Hubble was looking at different galaxies, and he constructed the Hubble law, which actually tells us about the expansion of the universe. He also tried to classify the galaxies based on these observations, and and we can see that the different kind of galaxy shapes are there for different kind of galaxies. So he constructed one classification diagram which is known as Hubble's tuning fork diagram, which contains actually initial level, which contains four categories. One is elliptical, which did not have, which are like spherical or spheroidal shape, which did not have any spiral arms. And then we have the lenticulars, which have uh, the spheroid bulge part as well as some amount of disk. And we have the spirals galaxies, which have some spiral arms and which are again divided into two parts. See, one is barred spiral, the lower one, and the upper one is normal spiral galaxies. So barred spiral galaxies actually they contain some bar in between, and there were some irregular type of galaxies which does not fit into any kind of these galaxies actually, and they were known as the irregular galaxies. So to study the morphology of this type of galaxies, actually the astronomers use different kind of data analysis techniques. One is known as the uh, isophote fitting, and that is like the dividing the decomposing the galaxy image into some surface brightness parameterization profiles using some isophotes, and then they can know about different part of the galaxies. So this is one of the image in the left, and when the isophotes which actually uh, selects the same brightness points and forms these control like structures, actually they are having the same brightness, same surface brightness points, and from there actually you can know many things which I'm not going in details right now. Now one very important point that actually I want to mention is like what is the use of the larger telescopes. So the use of the larger telescope is that the larger telescope actually collects more light and allow you to see greater details. So angular resolution of the telescope actually can be related to this formula, which actually relates the wavelength of observation as well as the diameter of the telescope. So we can see that for a wavelength of 580 nanometer, like in yellow light, to achieve a resolution of 0.1 arc second, we need a aperture telescope which actually have which must be minimum aperture size of 1.2 meter. So here we can see that if we have a very large aperture telescope, we can gather more light and more detail. So these are two important points we need to remember. So with that idea, actually, the astronomers actually trying continuously to develop bigger and bigger telescopes. So this picture actually uh, gives an idea about the telescopes that are being already built and are currently in making. So here we can see that the larger two uh, disc, they are actually the size of the uh, primary mirror. Actually, in this case, the 30-meter telescopes and extremely large telescopes, they are already, the construction is going on. And right now we have like the most biggest or telescopes is in this southern hemisphere is the VLT, or the very large telescopes. So actually, in Chile, there is actually organization known as European Southern Organization, which actually is a collaboration of 16 countries, European countries, which actually are maintaining this type of telescope or building bigger telescopes. So we can see that these are the ESO telescopes which are available in Chile, and mostly they are in these red points in the map in the Chile, and which are in the Atacama region. So one important telescope is the Very Large Telescope, which is the world's most advanced visible light astronomical observatory right now, which can observe more than 340 nights per year in mostly visible and near infrared regions. So actually, this was a ESO, European Southern Observatory Telescope, and they actually focused on design, construction, and operation of the powerful ground-based observing facilities. And this Very Large Telescope actually contained and the four bigger telescope, which is 8.2 meter diameter, and four smaller telescopes that we can see they are 1.8 meter, and one telescope which is 4.1 meter, which is at the back, and this is responsible for discovering many important results in astronomy, including some exoplanets. So here we can see one nearby view of the VLT telescope. And another picture here, we can see that there's one laser going on from the VLT. So this is very important. Many people actually access this question to me, like what you do with what the astronomers actually do with the help of this laser. So that is a very important point, because nowadays with the in the large telescope, actually they uses one technology that is known as adaptive optics, and this actually laser us to create some artificial stars in the sky so that the atmospheric turbulence can be reduced. So here we can see that when one wave front is coming from the star light, and that gets distorted due to the turbulence of in the atmospheric layers. So the adaptive optics actually they changes the primary changes the secondary mirror in the telescope according to the change of the turbulence of the atmospheres, and that actually helps in stabilization of the images. So VLT of ESO was the first telescope actually to get the laser guide star adaptive optics facilities in the southern hemisphere, and very significant actually results have been achieved with the implementation of this type of technologies. One is this: we can see that without adaptive optics, it was not so possible to get so distinct pictures or the images uh, of the stars or galaxies. But with the adaptive optics, we can have very clear images. And some bigger upcoming telescopes are being built in Chile. One is known as Giant Magellan telescope. So that have actually 7 telescopes combined, actually of 8.4 meter diameter, and it will observe it will get the first light in 2029. And another one is ELT, that is known as Extremely Large Telescope, that has aperture of 39.3 meter, which is very huge. You can see here in the picture, the leftmost is the Extremely Large Telescope, and that is being built. As compared to other telescopes, this is larger, and we expect that when it will be completed, we get some more good pictures or data about the universe. So coming to the exoplanet, actually we have many exoplanets right now, but until 1991 there was no exoplanet detected. And then in 1992, actually there were 2 exoplanets detected orbiting a pulsar star. That is particularly important because that actually tells us that the planets may be formed in different scenarios, because the pulsar is the after the explosion of the supernova actually the remaining thing that was available there, actually that there the planet just formed. So it actually challenges the existing theories of planet formation also. That way that is significant. And later until 2000 we have 46 exoplanets, but right now we have more than 5,000 exoplanets, and you can see here. And there are various exoplanets detection methods to detect the exoplanets. Mostly they observe the light as well as the gravitational lensing and some movements. And one successful method was radial velocity method, which measure the slight changes in the host star's movement, which is also known as the wobble. And that actually can be seen in the spectrum. So because of the Doppler shift. So this is an indirect way to detect the exoplanets, because the direct ways are very challenging to detect exoplanets. And so uh, because the light of the exoplanet that is very low as compared to the host star, so that's why we need to rely on this type of indirect methods. And once one exoplanet is detected, there are multiple follow-up observations through different telescopes to study the exoplanet. So another method is known as gravitational microlensing, that uses the effect of the gravity on the light as a probe to detect the exoplanets. This is very extremely sensitive and can detect low mass exoplanet also. If there is one planet there, then we can see some spikes like this, and then we need to get some follow-up observations. And another one is the direct imaging, where we actually the astronomers actually use some coronagraph to block the starlight, and for a longer duration of time, if we observe, then uh, we can see the exoplanets. But it is very difficult to image because of the high intensity of the light of the host star. Another one is the astrometric method, which is the movement of the planet star system. If a star contains exoplanets, then the movement will be different, which can be detected uh, if we observe for a longer duration of time. And so there are some non-popular methods also, which are like pulsar timing variations, and I'm not going detail into these things. So these are also not so popular because they were not so successful in detecting so many exoplanets, but they have confirmed some exoplanets of already detected exoplanets. So the most successful methods of detection of the exoplanet is the transit methods. That is, we can see that if a planet moves around a star, and if we can observe, then we can see that the starlight gets dimmed. So that is the most successful methods in detecting maximum number of exoplanets so far. So we can see that for bigger planets, the light blockage is more, so we can have more transit signal. And the transit light curve like this, which is actually uh, the depth of the transit, which is given by the delta, that actually gives us the ratio of the star ratio of the planet to the ratio of the star. Because if we have a very bigger planet, we have more blockage of the starlight, as I mentioned, then the transit depth will be more. So we can extract many information from this transit light curve, uh, and these are mostly the photometric parameters. And once the photometric parameters like the inclinations and other radius mass, etc., are determined, we can estimate the mean densities, and which will be helpful in studying the structure and formation of the exoplanets. So this is a important point, but there are some challenges to observe these things. We theoretically we expect some flat bottom in the transit light curve, but due to the limb darkening, we actually get we do not get flat transit bottoms. It is because the photons has to follow a more oblique path when coming from the limb of the star, making the stellar disk appears to be brighter at the center. So that is a challenge. We need to take care of this while modeling. Another important point is the star spots. Sometimes some star contains some star spots which actually uh, moves in arbitrary directions. That actually we can see here. So it is difficult to model the exoplanet transit light curve when the star has star spots. So because it affects the entire transit light curve and the transit depth also, so our estimation will be difficult. So in this case, actually, the most successful in detection of maximum number of transiting exoplanet was through the TESS, which is a transiting exoplanet survey satellite, which actually detects exoplanet. That once the exoplanet is detected, the ground-based follow-up observations are done. So here I have downloaded the exoplanet light curve data from the TESS archive for this WASP 104 system, where we can see that the colorful top panel is the TESS data, which needs to be normalized to make it the flux needs to be normalized to calculate the periods. And then once the period is calculated and we get the period like this, and then we need to perform some binning to get the transit properly, and then we can model the transit light curve like this. And here I have modeled the data using a code known as the prism, which was developed by one of our professors here. Actually, this code is very important because it can simultaneously model the limb darkening as well as the star spots. So it can give us the accurate results. And we can see that I have compared the results with some literature and it is matching. So another question comes like, what about the planetary atmosphere and habitability when we study the exoplanets? But that is, I think, beyond the scope of this talk because this requires some uh, theoretical models, atmospheres to fit to the data, and we require also transmission spectrums. Then only we can decide that if that planet can be habitable or not, and we need to confirm first these things. So I'm skipping this. So finally, coming to an end, actually the fundamental questions again remain same, like what is in the sky. Now we know little bit about the objects in the present in the sky. Still, there are many more questions that were unanswered, and many unknowns are yet to explore, and many more to go. So that questions always will remain with the humanity. So these are all from my side. So there is a one slide for the students where I am trying to tell about something like how you can start if you are interested in astronomy. What I think is like you need to develop your interest first. You need to be curious and organized. Then you can follow your track and you will be successful that way. So one important point is that right now the NCRA TIFR is accepting applications for the summer research program, visiting student research program. So those who are interested and eligible, I request to apply. The deadline is coming. It is February 15th. And also to start with the projects, you can visit this website, which actually contains some citizen science projects, which can be done at the very first beginning stage. And if required, you may contact me. I am available. My email address is given there. So thank you.
Thank you so much for the talk. Actually, it was an amazing talk. Uh, so participants, if you have any questions or any queries, you may go ahead and ask him. Yeah, you can unmute yourself and ask him.
Good evening, sir. It is Pratiksha speaking. Actually, I
Yes.
wanted to ask a question. It is quite a trending topic in today's astronomy sphere. It is about the ZTF comet.
Yes.
Actually, I wanted to ask, I know how to view the comets. Usually, you need to go be in dark places and away from the city lights. But
Mhm.
being in Indian cities, there is not really much of a chance. So, is there any possible way to view the comet in Indian cities?
Oh, actually, I'm not so sure about the exact location from where you can observe this comet. But recently, in the last week, I saw in the news that in the February month, it will be visible in many part of the uh, India, I think. So, my suggestion is to look into, please look into those things. Then you will get to know because I'm not so sure about it.
Yes, thank you, sir.
Yeah,
Okay.
thank you, Pratiksha. Probably, if I may add to Debashish, if there is any such visibility of comets, probably you might contact the Planetarium Guwahati. They usually organizes these programs frequently. You may contact the authority there. Probably they'll be able to tell you in a much deeper detail. Okay, any other questions from the audiences? Please ask. If even if you're not comfortable in English, please feel free to ask in your language which you're comfortable with.
অসমীয়াটো সুধিব পাৰে।
Okay, I think Debasish, তুমি অলপ তোমাৰ জাৰ্নিটোৰ বিষয়ে কৈ দিয়া নহলে, how did you end up in your current research institute, so that they might also get some ideas about it.
Actually, after masters মই ট্ৰাই কৰি আছিলোঁ বহুত কেইখন ইনষ্টিটিউশ্যনত, এণ্ড এট দ্য টাইম দুখনমানৰ পৰা চিলেকশ্যন আহিছিলে, কিন্তু প্ৰব্লেমটো হৈছিলে ফাণ্ডিং ৰিলেটেড আৰু অকণমান অসুবিধা হৈছিলে এইটো সময়ত ক'ভিডৰ কাৰণে। দেন এইখন ইনষ্টিটিউটৰ পৰা কলটো পালোঁ। তাৰপিছত ক'ভিডৰ কাৰণে বহুত দিন আহিবও পৰা নাছিলোঁ। তাৰপিছতে ভিজাৰ প্ৰব্লেম হৈছিলে, তো গুৱাহাটীৰ পৰাই কাম কৰি আছিলোঁ। তাৰপিছত যেতিয়া এইখিনি গোটেইখিনি অভাৰ হ'ল তেতিয়া আহিব পাৰিলোঁ। আৰু একচুৱেলি যদি তোমালোকে ভাবিছা এনেকৈ ইনষ্টিটিউশ্যনত ক'ৰবাত এপ্লাই কৰোঁ বুলি, তেতিয়াহ'লে মষ্টলি ইন ইণ্ডিয়া, একচুৱেলি মই ইয়াতে মেনশ্যনো কৰি দিছোঁ, তোমালোকে একচুৱেলি এক্সামছ আৰু ইণ্টাৰভিউ এইকেইটা ক্লিয়াৰ কৰিব লাগিব। আৰু বাহিৰত তোমালোকে যদি ইণ্ডিয়াৰ বাহিৰত এপ্লাই কৰোঁ বুলি ভাবা, তেতিয়াহ'লে কাণ্ট্ৰি ৱাইজ চবৰে ৰিকুৱাৰমেণ্টবিলাক বেলেগ বেলেগ। কিছুমান কাণ্ট্ৰিয়ে তোমাৰ IELTS GRE স্ক'ৰ বিচাৰে, আৰু কিছুমান কাণ্ট্ৰিয়ে তোমাৰ সেইখিনি নিবিচাৰে, প্ৰজেক্ট বিচাৰে বা প্ৰজেক্টৰ এক্সপিৰিয়েঞ্চ বিচাৰে বা এনেকুৱা ধৰণৰ পাব্লিকেশ্যন বা এনেকুৱা ধৰণৰ বস্তুবিলাক বিচাৰে। আৰু গোটেইখিনি আই থিংক নাও তোমালোকে য'তে ইণ্টাৰেষ্টেড হোৱা ইউটিউবত বিচাৰিলে গোটেইখিনি ডিটেইলছ পাই যাবা। আৰু মই ছাজেষ্ট কৰোঁ তোমালোকে ইণ্ডিয়াতে কাম কৰা বা বাহিৰতে এব্ৰডতে কাম কৰা, তোমালোকে এতিয়া আণ্ডাৰ গ্ৰেজুৱেট বা মাষ্টাৰ্ছত থকাৰ পৰাই অলপ অলপকৈ সৰু সৰুকৈ, যেনেকৈ মই ইয়াতে মেনশ্যন কৰি দিছোঁ, তেনেকুৱা প্ৰজেক্ট কিছুমান কৰিব পাৰা। আৰু তোমালোকৰ এক্সপিৰিয়েঞ্চটো তেতিয়া বিল্ড আপ হ'ব। আৰু বহুত ইণ্টাৰেষ্টিং হয় ছাবজেক্টটো, এষ্ট্ৰনমি, এষ্ট্ৰফিজিক্স, আৰু বহুত কাৰেণ্টলি বহুত গ্ৰ'য়িং হৈ আছে, তোমালোকে দেখিছাই। গতিকে মোৰ ছাজেশ্যনটো হ'ল, তোমালোকে যদি ইণ্টাৰেষ্টেড হয়, যিমান সোনকালে পাৰা সৰু সুৰাকৈ প্ৰজেক্ট হওক, ৱৰ্কশ্বপ হওক বা এক্সাম প্ৰিপেৰেশ্যন হওক, সোনকালে ষ্টাৰ্ট কৰি দিয়া। সেইটোৱে কথা আৰু।
Okay, thank you, Debashish. I think we have a question from
Debasish, I have a more question আছে।
Yeah, please.
কোৱেশ্চনটো হ'ল যে তুমি এটা কথাত ক'লা যে এক্সোপ্লেনেট প্ৰথমে 1992 দুটা এক্সোপ্লেনেট পাইছে, তাৰপিছত তোমাৰ টপিকটো চাগে এক্সোপ্লেনেটৰ ওপৰতে ন, ডিটেকশ্যন, এক্সোপ্লেনেট ডিটেকশ্যন,
মানে টপৰ টপিকটো নে?
মানে এক্সোপ্লেনেট ডিটেকশ্যনৰ ওপৰতে হয় নেকি তোমাৰ টপিকটো?
মানে
He is
মোৰ
a top-
PhD ৰিচাৰ্চটো নে?
correct, correct.
মোৰ একচুৱেলি অবজাৰভেশ্যনেল এষ্ট্ৰনমি, চ' ইয়াতে মেইনলি
আচ্ছা
এক্সোপ্লেনেট আৰু ষ্টেলাৰ আৰু গেলেক্টিক এই গোটেইকেইটাতে কাম কৰিব লগা হৈছে।
আচ্ছা আচ্ছা, নাই মোৰ এটা বেচিক কুৱেশ্যন আছিলে, মানে জাষ্ট এনে আউট অফ কিউৰিয়চিটি সুধি আছো এইটো, যে আজিলৈকে মানে এক্সোপ্লেনেটটো মানে কিমান দূৰৰ এক্সোপ্লেনেটটো আজিলৈকে মেক্সিমাম ডিটেক্ট কৰা হৈছে, মানে কিমান লাইট ইয়েৰ দূৰলৈকে কৰা হৈছে সেইটো?
I think the most distant exoplanetটো একজেক্ট মই ৰিচেণ্ট ফিগাৰটো মোৰ মনত নাই, কিন্তু
আচ্ছা
40 লাইট ইয়াৰ্ছ ডিষ্টেন্সত আমাৰ হেবিটেবল জোনৰ এক্সোপ্লেনেট ডিস্কভাৰ হৈছে।
আচ্ছা আচ্ছা, তেতিয়াহ'লে মানে ৰেঞ্জটোতো উইথ টাইম আৰু বাঢ়িব চাগে ন?
হয় হয়, উইথ টাইম বাঢ়িব। আৰু ইণ্টাৰেষ্টিংলি তোমালোকে যদি ইয়াতে নাসা এক্সোপ্লেনেট আৰ্কাইভটো নটিচ কৰি থাকা, এভৰি উইক নতুন নতুন এক্সোপ্লেনেট এড হৈ গৈ আছে। ইয়াতে মই ক'ৰবাত চাগে এটা বস্তু মেনশ্যন কৰিছিলো, মই যেতিয়া এক্সেছ কৰিছিলো সেইটো তেতিয়া ডিচেম্বৰ আই থিংক 17 নে কিবা এনেকুৱা আছিলে। সেইটো ডেটত 5020 আছিলে।
মানে এভৰিডে ইয়া এভৰি মান্থ মানে বাঢ়ি থাকেতো?
হয় হয়, আৰু মষ্টলি কি হয়, এই যিবিলাক তোমাৰ স্পেচ বেছ টেলিস্কোপ আছে, ফৰ এক্সাম্পল এইটো এটা টেষ্টটো আছে, বা এতিয়া তোমাৰ JWST ষ্টাৰ্ট কৰিছে, ত' ইয়াতে কি কৰে সিহঁতে তেতিয়াই অবজাৰ্ভ কৰি কিবা এটা ডিটেকশ্যন পাই লগে লগে সিহঁতে মানে কি কৰে, এটা কমিউনিটি আছে, তেওঁলোকে গ্ৰাউণ্ড বেছ অবজাৰভেটৰী বিলাকক জনাই দিয়ে, আৰু গ্ৰাউণ্ড বেছ অবজাৰভেটৰী বিলাকে লগে লগে ফ'ল' আপ অবজাৰভেশ্যন কৰে ইউজিং অল দ্য এভেইলেবল টেকনিক্স। আৰু ডিফাৰেণ্ট টেকনিকৰ পৰা কনফাৰ্মেশ্যন হোৱাৰ পিছতহে এক্সোপ্লেনেট বুলি কনফাৰ্মেশ্যনটো হয়, আৰু তেতিয়াহে আৰ্কাইভটোত লিষ্টিং হয়। গোটেই প্ৰচেছটো তেনেকুৱা ধৰণৰ, মানে অকল এটা টেকনিকৰ ওপৰত বা এটা মেথডৰ ওপৰত ৰিলাই কৰি পেলাই ডিটেক্ট কৰি নথয়, কাৰণ আমি ইয়াতে দেখিছোৱে, মই আগৰ শ্লাইডখনতো দেখাইছো, এনেকুৱা ষ্টাৰ স্পটৰ এনমেলি কিছুমান প্ৰব্লেম আছে আৰু ডিম ডাৰ্কনিকৰ প্ৰব্লেম আছে। য়েছ, চ' কেতিয়াবা আমি ষ্টাৰ স্পট এটাকে এক্সোপ্লেনেট বুলি চাই আছো, এনেকুৱাও হ'ব পাৰে। সেই কথাবিলাকৰ কাৰণে মানে যিমান পাৰি মেক্সিমাম নাম্বাৰ
ভেৰিয়াছ ফেক্টৰবোৰ চাই তাৰপাছত এইটো কনচিডাৰ কৰা হয় যে ইট ইজ এক্সোপ্লেনেট।
হয় হয় হয়, সেইটোৱে।
Okay, thank you, Pintu. Debasish, আৰু এটা question এটা আছে. So, Sikha has asked the question, what is the advantage of radio telescope over optical telescope?
Yes, radio telescope, actually these are longer wavelength telescopes. Like radio is the most longer wavelength, so in optical actually mostly we get the information about the outermost surface of the stars or the galaxies, but in radio we can look into more deeper, like the sometimes core or some other anomalies are there in the galaxies. So those things can be possible to observe through radio telescope. So these are the advantages.
Also, I'd like to add that with radio telescope, এনেকা ৰাতি নাচালে হয়. So
Yes.
দিনে ৰাতিয়ে you can view it at all times. I mean, use the telescope at all times. But optical telescopes, you need the dark sky. So দিনত তাৰ একো use নাই মানে.
Usually মই ৰেডিঅ'ত এতিয়ালৈকে কাম কৰা নাই বাৰু, মই অপটিকেল আৰু ইনফ্ৰাৰেড ডাটাতে কাম কৰিছোঁ। কিন্তু ইয়াতে আমাৰ ওচৰতে আটাকামাৰ লাৰ্জ মিলিমিটাৰ এৰে টেলিস্কোপ বুলি এটা টেলিস্কোপ আছে, সেইটো ৰেডিঅ' টেলিস্কোপ হয়, আৰু সেইটো টেলিস্কোপে আগতে বহুতখিনি ইম্পৰ্টেণ্ট এষ্ট্ৰনমিকেল অবজেক্টছ ডিস্কভাৰ কৰিছে, আৰু বহুতখিনি নতুন চাইন্স ওলাইছে সেইটো টেলিস্কোপৰ পৰা, তেনেকে বুলি কয় আৰু মই গম পাওঁ।
Hopefully আমি এইটো টক চিৰিজত এটা টক ৰেডিঅ' এষ্ট্ৰনমিৰ ওপৰতো ৰাখিব পাৰিম। আমি চাই আছো বাৰু স্পিকাৰ। So yeah.
So any more questions? Kindly, yeah, there is one more question from Mr. Ankur Jyoti Bora. So he has asked, what are the advantage of infrared telescope?
Yes, infrared telescope actually infrared light to এনেকুৱা হৈছে যিবিলাক cold object বিলাকে emit কৰে. For example, আমি molecular cloud study কৰিব লাগে for example. তেতিয়া molecular cloud টো observe কৰিবলৈ হ'লে আমি opticalৰে observe কৰিলে বা বেলেগ এটা wavelengthত observe কৰিলে নহ'ব মানে। তো তেতিয়া আমি এইটো কাৰণ সি cold হয় আৰু তো সি ইমানখিনি cold হয় যে সি অপটিকেলত ইমিট নকৰে, গতিকে আমি ইনফ্ৰাৰেড দি পেলাই চালে তাক সেইখিনি ডিটেইলছ গম পাব পাৰি। আৰু ইণ্টাৰেষ্টিংলি এনেকুৱা ধৰণৰ মলিকুলাৰ ক্লাউডৰ নিচিনা অবজেক্ট বিলাকত কি হয়, ডাষ্ট গ্ৰেইনৰ বহুত এফেক্ট থাকে, য'ত মানে ষ্টাৰ ফৰ্মেশ্যন হৈ থাকে, এনেকুৱা ধৰণৰ পৰিঘটনাবিলাক হৈ থাকে। গতিকে সেই ডাষ্ট গ্ৰেইনৰ ৰিলেটেড ষ্টাডি বিলাকতো ইনফ্ৰাৰেডটো যথেষ্ট গুৰুত্বপূৰ্ণ হয়। আৰু লগতে এতিয়া ৰিচেণ্টলি এক্সোপ্লেনেটৰ এটমস্ফেয়াৰ ৰিলেটেড ষ্টাডি বিলাকতো ইনফ্ৰাৰেডৰ বহুতখিনি ইউজ হ'বলৈ আৰম্ভ কৰিছে। ৰিচেণ্টলি মই চাই আছিলোঁ, তাতে পাইছিলোঁ এনেকুৱা ছালফাৰ ডিটেকশ্যন বা এনেকুৱা ধৰণৰ কিছুমান এলিমেণ্ট আছে যিখিনি এলিমেণ্টে ভলকেনিজিম সিগনিফাই কৰে। চ' সেই তেনেকুৱা ধৰণৰ ডিটেকশ্যন বিলাক ইউজুৱেলি কৰিব পৰা যায়। কৰাৰ লগে লগে যদি আমি কনফাৰ্ম হওঁ যে তাতে সালফাৰ আছে, তেতিয়াহ'লে that means that exoplanet contains some volcanic activities, আৰু সেই volcanic activities টো কনফাৰ্ম হোৱাৰ পিছত এই গোটেইখিনি আকৌ এটা নতুন ব্ৰাঞ্চ এষ্ট্ৰনমিত ডেভেলপ হৈছে, এষ্ট্ৰজিঅ'লজি বুলি কয়। মানে জিঅ'লজি আৰু এষ্ট্ৰনমি মিক্স আপ কৰি পেলাই তেওঁলোকে ষ্টাডি কৰিব বিচাৰে কেনেকে হৈ আছে। চ' এই ধৰণৰ বস্তুবিলাকত যথেষ্ট হেল্পফুল হয়।
ইনফেক্ট ৰিচেণ্টলি যিটো JWST লঞ্চ হৈছিলে সেইটো ইনফ্ৰাৰেড টেলিস্কোপে হয়। চ' এণ্ড ৰিচেণ্টলি পেপাৰ এখনো আহিছে সেই ছালফাৰ ডিটেকশ্যনৰ এটা এক্সোপ্লেনেটৰ। So in fact, participants can look into that if you're interested in that.
Yeah. Okay, so thank you, Mr. Ankur Bora. So there is, since we have started talking about James Webb Space Telescope, so there is one more question. Mr. Akash Hazarika, he has asked, sir, why are gold foils used in JWST?
Actually, gold foil to যিকোনো টেলিস্কোপতে ইউজ হয়। এটোটো it is like a heat shielding হিচাপে ইউজ কৰা যায়। তো আমাৰ অকল তাতে বুলি নহয়, আমাৰ আমি ইউজ কৰি থকা লেপটপ বিলাকৰ ভিতৰতো কিছুমান কম্পোনেণ্ট থাকে যিবিলাক গোল্ড ফইল দি পেলাই কভাৰ কৰা থাকে। তেনেকে আমাৰ গ্ৰাউণ্ড বেছ টেলিস্কোপ বিলাকতো তেনেকুৱা আছে। তো কিন্তু জেমছ ৱেবৰ এইটো কথাটো বহুত মিডিয়াতো আহিছে বা বহুত নিউজতো ওলাইছে, বিকজ তাৰ ডিজাইনটো এনেকুৱা ধৰণে কৰা হৈছে, মানে তাত সেইটো অলপ এক্সপ'জ হৈ থাকে। সেইটো কাৰণে বহুতখিনি মানুহে গম পাইছে যে এনেকে গোল্ড ইউজ কৰে বুলি। তো মেইন ৰিজনটো এইটো।
So basically, মানে কি হয় যে গোল্ডে হিটটো সোনকালে ৰেডিয়েট কৰি উলিয়াই দিয়ে। So maybe the components of the telescope, it remains protected because of that. সেইটোৱে হয় নে বাৰু দেৱাশিষ?
I think shielding হে নেকি? Shielding নেকি most probably.
Okay.
নে radiate কৰি ওলাই দিয়ে।
নাই, shielding যে কলা কথাটো, maybe some people they might not be sure about the word shielding, মানে exactly কি বুজায় সেই বস্তুতে?
Actually, ইনফ্ৰাৰেডটো হৈছে কি, JWST টো ইনফ্ৰাৰেডত ইউজ হয় ন। চ' ইনফ্ৰাৰেডটো বহুত চেঞ্চিটিভ হয়। মই কৈছোঁ এতিয়া, যিহেতু বহুত ক'ল্ড টেম্পাৰেচাৰ, যিহেতু মানে বহুত ল' টেম্পাৰেচাৰ অবজাৰ্ভ কৰিব লাগে, যিহেতু সেইকাৰণে কি হয়, সিহঁতে যিমান পাৰি লোৱাৰ টেম্পাৰেচাৰত ৰাখিলে টেলিস্কোপটোত আমি ডাটাবিলাকত নইজ কমকৈ পাওঁ। গতিকে যদিহে বহুত ল' টেম্পাৰেচাৰত ৰাখিব লগা হয়, তেতিয়াহ'লে আমাৰ কচমিক ৰে হিটিং থাকে, চ'লাৰ ছানৰ ৰেডিয়েশ্যন থাকে। তো সেই গোটেইবিলাকৰ পৰা তাক বচাবৰ কাৰণে তাক মানে হিটৰ পৰা ৰেজিষ্ট কৰিব লগা হয়। সেইটো কাৰণে একচুৱেলি ইউজ হয়। ত' সি মানে চিল্ডৰ নিচিনাকে কাম কৰে, মানে কভাৰ এটা নিচিনাকে সি ৰিফ্লেক্ট কৰি পেলাই পঠাই দিয়ে, মানে সোমাব নিদিয়ে মানে সেইখিনি যিখিনি কচমিক ৰে হওক বা এইফালে ছানৰ ৰেডিয়েশ্যন হওক সেইখিনি।
Okay. I think it's clear now. Thank you, Mr. Akash Hazarika. So there is one more question, Debasish. So Mr. Neil Pawan Kakoti. So it's an interesting question. So he has asked, like, sir, after discovering an exoplanet, how can we know about the habitat of that? I mean, what are the techniques astronomers used? So he wants
Yes,
to, yeah, okay, fine. Go ahead, Debasish.
this is a very interesting question. Actually, that part I skipped here. Actually, this is the thing. আমি কি কৰিব লাগে যেতিয়া এক্সোপ্লেনেট এটা ডিটেকশ্যন হয় তাৰপিছত এক্সোপ্লেনেটটোৰ এতিয়া মই যিমানখিনি ইয়াত এক্সপ্লেইন কৰিলো ইয়াৰ আগৰখিনি কথা এই গোটেইখিনি বস্তু একচুৱেলি ফটোমেট্ৰিক অবজাৰভেশ্যন চ' চিমিলাৰলি মই আগতে ফাৰ্ষ্ট বিগিনিঙৰ শ্লাইড কেইটামানত দেখাইছিলো যে আমি দুটা ধৰণে এষ্ট্ৰনমিকেল অবজেক্টবিলাক ষ্টাডি কৰিব পাৰোঁ এটা হৈছে লাইটটো আৰু এটা হৈছে আমি স্পেক্ট্ৰাটো ল'ব পাৰোঁ এতিয়া এই ধৰণৰ এটমস্ফিয়াৰ ষ্টাডি কৰিবলৈ হ'লে আমি কি কৰিব লাগে ট্ৰেনজিট স্পেক্ট্ৰস্কপি কৰিব লাগে ট্ৰেনজিট স্পেক্ট্ৰস্কপি মানে যেতিয়া এক্সোপ্লেনেটটোৱে ষ্টাৰটোক হোষ্ট ষ্টাৰটোৰ চাৰিওফালে ঘূৰিব সি এবাৰ আমাৰ ফ্ৰণ্টত থাকে এবাৰ হোষ্ট ষ্টাৰটোৰ পিছফালে থাকে তো সেই আমাৰ ফ্ৰণ্টত বা হোষ্ট ষ্টাৰ আৰু আমাৰ মাজত যেতিয়া থাকিব তেতিয়া আমি যদি ট্ৰেনজিট স্পেক্ট্ৰস্কপি কৰোঁ তেতিয়াহ'লে সেই হোষ্ট ষ্টাৰটোৰ পৰা যিখিনি লাইট আহিব সেই লাইটখিনি এক্সোপ্লেনেটটোৰ এটমস্ফিয়াৰৰ মাজেদি পাছ হৈ আহিব আৰু সেইটো ট্ৰেন্সমিশ্যন স্পেক্ট্ৰস্কপি সেই ট্ৰেন্সমিশ্যন স্পেক্ট্ৰস্কপিটোৱে আমাক কি দিব তাৰ এটমস্ফিয়াৰটোৰ ইনফৰমেশ্যন দিব ঠিক তেনেকে যেতিয়া সি পিছফালে থাকিব এক্সোপ্লেনেটটো তেতিয়াও আমি এটা আমি ল'ব পাৰোঁ তেতিয়া সি আকৌ কেইটামান বেলেগ চিগনেচাৰ দিব তো আল্টিমেটলি কি হয় আমি যেতিয়া স্পেক্ট্ৰামকেইটা ল'লো এবাৰ আমি ফ্ৰণ্টত যাক আমি ট্ৰেনজিট বুলি কওঁ আৰু এবাৰ পিছফালে থাকে সেইটো অকালটেশ্যন বুলি কয় তেতিয়া আমি ট্ৰেন্সমিশ্যন স্পেক্ট্ৰাম দুটা পাম এতিয়া সেই ট্ৰেন্সমিশ্যন স্পেক্ট্ৰাম দুটাৰ লগত কি হৈছে আমাৰ প্লেনেট ফৰ্মেশ্যন আৰু প্লেনেটৰ এটমস্ফিয়াৰৰ কিছুমান মডেল থিয়ৰিটিকেল মডেল আছে সেইখিনি আমি কি কৰিব লাগে আমাৰ এক্সিষ্টিং স্পেক্ট্ৰামৰ ডাটাৰ লগত ফিট কৰিব লগা হয় আৰু ফিট কৰিলে আমাৰ কি হয় আমি সেই প্লেনেটটোৰ কেমিকেল কম্পজিশ্যন পাই যাওঁ আৰু কেমিকেল কম্পজিশ্যনটো আমি ইউজুৱেলি কি কৰা যায় আমাৰ আৰ্থৰ যিখিনি এটমস্ফেৰিক কেমিকেল কম্পজিশ্যন আছে তাৰে আমাৰ ডেটাৰ লগত আমি মেটচিং কৰাওঁ মেটচিং কৰালে আমি গম পাওঁ যে ইয়াত হেবিটেবিলিটি চান্সেছ কিমান তো ইণ্টাৰেষ্টিংলি মই যিটো মেনশ্যন কৰিছিলোঁ ট্ৰাপিষ্ট বুলি চিষ্টেমটো আছে ট্ৰাপিষ্ট 1E বুলি যিটো চিষ্টেম আছে একচুৱেলি সেই ট্ৰাপিষ্ট সোলাৰ চিষ্টেম আমাৰ সোলাৰ চিষ্টেমৰ নিচিনাই চিষ্টেম হয় সিহঁতৰ মানে 5 নম্বৰ এক্সোপ্লেনেটটো সি বহুতখিনি পাৰ্চেণ্টেজ মোৰ দেন আই থিংক 90% মান এটমস্ফেৰিক মেটচিং আমাৰ আৰ্থৰ লগত আছে গতিকে সেইটো এটা হেবিটেবল প্লেনেট এইটো 40 লাইট ইয়াৰ্ছ ডিষ্টেঞ্চত আছে তেনেকুৱা ধৰণে একচুৱেলি কৰা হয় আৰু মই পাৰ্চনেলি এইখিনি কাম এতিয়ালৈকে মই কৰা নাই আৰু এইখিনি একচুৱেলি অলপ কেমেষ্ট্ৰি ৰিলেটেড কথাও আহে মই এতিয়ালৈকে ফটোমেট্ৰি এক্সোপ্লেনেটত ফটোমেট্ৰিয়ে কৰিছোঁ আৰু বাকী ষ্টাৰ আৰু গেলেক্সিতহে স্পেক্ট্ৰস্কপি কাম কৰিছোঁ মই সেইখিনিহে গম পাইছোঁ আৰু যিখিনি মানে তোমাক ক'লো
Thank you. I think that was really an interesting topic. So probably, yeah, there is one more question from Anubhuti Sharma. So it's related to the research part actually. So he's asking, like, please name the examinations to get admissions in such institutions. I mean, probably he's asking about your institution, Debasish. So please tell him.
Actually, ইয়াত আমাৰ ইনষ্টিটিউশ্যনটোত ইয়াৰ কাৰণে কি হয় প্ৰথম এটা প্ৰপ'জেল পঠাব লাগে প্ৰপ'জেলটো পঠোৱাৰ পিছত যদি একচেপ্ট হয় তেতিয়া তেওঁলোকে ফৰ্মেলি এপ্লাই কৰিবলৈ কয় তাৰপিছত এপ্লাই কৰাৰ পিছত ইণ্টাৰভিউ হয় তো ইয়াৰ প্ৰচেছটো তেনেকুৱা আৰু এক্সট্ৰাকে একো লেংগুৱেজ বা এনেকুৱা ধৰণৰ ৰিকুৱাৰমেণ্ট নাই কিন্তু মোৰ ক্ষেত্ৰত মই ইমান চিয়'ৰ নাছিলোঁ মই বেলেগ ইনষ্টিটিউশ্যনতো এপ্লাই কৰিছিলোঁ আৰু বেলেগ কাণ্ট্ৰিটো সেইকাৰণে মই GRE আৰু IELTSটো দিছিলোঁ তো সেই এক্সাম দুটা দি থ'লে বহুতখিনি সুবিধা হয় আৰু মেইনলি যদি US-ত এপ্লাই কৰিবলগীয়া হয় তেতিয়াহ'লে US কানাডা আৰু বহুত কেইখন অষ্ট্ৰেলিয়ান ইউনিভাৰ্চিটিটো যে GREটো তেওঁলোকে বিচাৰে আৰু লগতে IELTS-টো বা TOEFL এই দুটাৰ ভিতৰত যিকোনো এটা ইংলিছ প্ৰফিচিয়েঞ্চিৰ কাৰণে এইটো হয় কিন্তু চিলিখন কি হয় স্পেনিছ স্পিকিং কাণ্ট্ৰিৰ কাৰণে ইয়াত ইংলিছৰ ইমান ধৰা বন্ধা স্ক'ৰ নাই সেইকাৰণে মোৰ অলৰেডি হায়াৰ ছেকেণ্ডেৰী আৰু ডিগ্ৰীৰ ইংলিছৰ পেপাৰ দুখনৰ মাৰ্কছটো ভাল আছিলে সেই দুখন তেওঁলোকে কনচিডাৰ কৰিছে আৰু IELTS-ৰ স্ক'ৰটো আছিলে বাৰু মোৰ কিন্তু একচুৱেলি সেই এনেকুৱা ধৰণে এইকেইটা এক্সাম দি থ'লে সুবিধা হয় আৰু
Okay, thank you, Debasish. I think Anup Jyoti has got his answer. So, are there any more questions, audience?
I think Fatima has raised her hand, so if you can unmute yourself and go ahead. Okay, maybe no. Okay.
So, can we expect any more questions? So, yeah, there is one more question from Mr. Ankur Jyoti Bora. So, he has asked, was there any chance to become the planet Jupiter as a star during its formation?
No.
Okay.
এইটো কি হৈছিলে, এইটো এটা আছে কন্ট্ৰভাৰ্চি এটা। অলপমান যদি মাছটো অলপমান বেছি হ'লহেঁতেন তেতিয়াহ'লে সি ফৰ্ম হ'লহেঁতেন, কিন্তু এইটো এনেকুৱা এটা মাছত সি ৰৈ গ'ল জুপিটাৰটো, যিটো সময়ৰ পিছত সি ফৰ্ম হ'বলৈ নোৱাৰিলে। কিন্তু সি যদি আৰু অলপ বেছিকে থাকিলেহেঁতেন, এটা লিমিট আছিলে, মই একজেক্ট ভেলুটো পাহৰিছো, তেতিয়াহ'লে কিন্তু এইটো চান্স আছিলে। কিন্তু এতিয়া ইন ফিউচাৰত এইটো নহয় আৰু, সি প্লেনেটে হৈ গ'ল আৰু।
Okay. Thank you. I think Ankur has got his answer. So, if I think it's time now to wrap up the session. So, what do you say, Himanshu?
Yeah. So the kiba queries thake, you can mail him. So
Yeah.
The email ID is in the first slide itself.
Exactly. Probably we'll also share his email ID.
Yeah.
And Debasish will be happy to assist all the questions. So I think it's now time for Dr. Pintu Burman. He'll be giving the vote of thanks to the speaker as well as the participants. Over to you, Mr. Pintu.
Thank you, Apurva. So I would like to thank Mr. Debasish Hazarika for kindly sharing his valuable time and explaining his research so confidently. So all of us could learn a lot from this talk, especially the coverage of the from very basics of astronomy in ancient days and its evolution to modern days. So also he explained briefly about the uses of CCD and also discuss about the classifications of stars from various factors. And finally, the measurement procedure of light from various stars and galaxies using the modern telescope is also very illuminating. So I'm sure the participants enjoyed it as well. So at the same time, I would like to offer my vote of thanks to the participant who took out time to attend the webinar. So it must have been a learning experience for them as well. So we hope that you will continue to support us in the future as well. So thank you. So that's it from my side. So it's over to you, Himanshu.
Yeah, thank you, Dr. Pintu Burman. So Debasish, if you don't mind, can we chip in two more questions because participant had asked there are two more questions.
No problem.
Okay. So this is Mr. Nilpavan Kakoti. So he has asked a simple question. So, sir, is there any chance of our sun to become a black hole? If so, why?
Actually, এইটো নহয়, কাৰণ কি এটা মাছ লিমিট আছে। এইটো আমাৰ ইণ্ডিয়ান সাইণ্টিষ্ট এজনে উলিয়াইছিলে, সুব্ৰমণ্যম চন্দ্ৰশেখৰ বুলি কয়। সুব্ৰমণ্যম চন্দ্ৰশেখৰে এটা মাছ লিমিট দি গৈছিলে, এইটো চন্দ্ৰশেখৰ মাছ লিমিট বুলি কয়। এতিয়া যদি আমাৰ চানৰ যিটো মাছ আছে, সেই মাছটোতকে যদি 1.4 টাইমছ বেছি হয় মাছ এটা ষ্টাৰৰ, তেতিয়াহ'লে সি নিউটন ষ্টাৰ হোৱাৰ চান্স থাকে। কিন্তু তাতকে আকৌ বহুতখিনি বেছি 15 টাইমছ 20 টাইমছ বা 30 টাইমছ এনেকুৱা বেছি হ'লেহে সি ব্লেক হোল হ'ব বুলি কনফাৰ্ম ক'ব পাৰি। গতিকে যিহেতু 1.4 টাইমছ বেছি হ'ব লাগিব মিনিমাম মাছ, গতিকে চান কেতিয়াও নহয়। চান আমাৰ সূৰ্যটো অকল হোৱাইট ডুৱাৰ্ফে হ'বগৈ এতিয়া, মানে ইন ফিউচাৰ।
Okay, okay. Thank you, Debashish. I think Ankur has got his answers, and the Ankur Jyoti Bora, he has asked, he has requested, in fact, to share your PPT. So, Debashish, will
No
you be able
problem.
to do so?
Yeah, no problem. I will share.
Okay, fine. Thank you, Debashish.
আৰু
And there
তোমালোকৰ
is
যদি
one.
কিবা থাকে মোক মেইল কৰিব পাৰা, মই যিমান পাৰো হেল্প কৰিবলৈ চাম। আৰু এনেকুৱা সৰু সুৰা প্ৰজেক্ট কিবা কিবি কৰিব পাৰা তোমালোকে ষ্টাৰ্টিঙৰ কাৰণে। আৰু যদি কিবা এক্সট্ৰা হেল্প লাগে তেতিয়াহ'লে মেইল কৰিবা, মই যিমান পাৰো হেল্প মানে সহায় কৰিব চাম। হিমাংশুৰ লগত কণ্টেক্টত আছে, তাকো শ্বেয়াৰ কৰি দিম, তোমালোকে কৰিব পাৰিবা।
Yes. Probably there are two more questions. So probably what we will do is that since we are finishing up, we will mail you the questions, Debashish. So
Okay.
probably Debashish will answer those questions and then they will get back to you. So I think it's time to wrap up, Himanshu. What do you say?
Yeah. So, any concluding remarks from Debasish da?
বহুত ভাল লাগিল এনেকে আজি ইমান লং টক আজি প্ৰথম দিছো। ইউজুৱেলি হাফ এন আৱাৰ 40 মিনিটছ মান থাকে, আজি 1.5 ঘণ্টামান হৈ গৈছে। এইটো এটা নতুন এক্সপিৰিয়েঞ্চ। আৰু ইউজুৱেলি টপিকবিলাক সৰু সৰু টপিক থাকে, আজি অকণমান টপিকটো ডাঙৰে, বহুতখিনি কথা ক'ব লগা হৈছে, বহুতখিনি কথা কভাৰ কৰিব লগা হৈছে। আৰু যিখিনি অডিয়েঞ্চ আছে তেওঁলোকে কুৱেশ্যনছখিনি যিখিনি সুধিছে সেইখিনি শুনি মোৰ লাগিছে যে তেওঁলোকে ইণ্টাৰেষ্ট পাইছে আৰু টপিকটো যিমানখিনি পাৰে বুজি পাইছে। সেইটোৱে ছাকচেছ বুলি ভাবিছোঁ। আৰু গোটেইখিনি অৰ্গেনাইজাৰলৈ থেংক ইউ, এনেকুৱা এটা ইনিচিয়েটিভ লৈছা তোমালোকে। মোৰ ফালৰ পৰা সেইখিনি।
Yeah, thank you, Debashish. So we would also like to wish you all the very best for your PhD, and I hope we will also get you, I mean, in the future as well for delivering such talks. So I think it was very interesting. And Himanshu, so shall we conclude now?
Yeah, I think we can conclude. Yeah.
Okay. Thank you, Debashish. All the very best, and please take
Best
care.
wishes, Debasish.
Thank you so much.